Okay, in this video, we're looking at another function where we again want to find the increasing and decreasing behavior. Increasing, decreasing. So this is currently written as a product, but I need not leave it as a product. We can multiply it out, so I don't have to use the product rule. So x to the 2/3 times x squared will be x to the 8/3, or 2 2/3. And x to the 2/3 times 9 would be 9 x to the 2/3. Okay, so that's our function rewritten a little bit nicer, so I don't have to use the product rule. And so now we can multiply that out, or we can work this out now as far as the derivative. And I'd ask you to pause the video and try to work the derivative yourself out. Get it in a nice cleaned up, simplified form. And compare that then to what I have. So the derivative, after we've worked it out and simplified, is going to be 8x squared minus 18 all over 3 cube root of x. 3 cube root of x. And now we want to figure out, okay, when is the derivative 0? When is the derivative undefined? So it's going to be 0 when the numerator is 0. It's going to be 0 when the numerator is 0. So when 8x squared minus 18 is 0. So this only works when you have a single fraction. It's one of the advantages of writing the fraction function as a single fraction. Because when we have a single fraction, we don't have to do all the other stuff that we might normally do to solve an equation involving fractions. We just have to look at the numerator and say, when's the numerator 0? And so we can solve that equation pretty easily. We have 8x squared minus 18 equals 0. We bring the 18 over, divide by 8. That would actually simplify to 9 over 4. And then apply square root to both sides. So remember, when we do square root, we're going to get plus or minus. So we get plus or minus 3/2. Now this time, we actually do have a time where the derivative is undefined. Or specifically, when we're dividing by 0. When we're dividing by 0. Right? And so that's going to happen when cube root of x is 0, which would happen when x is 0. So this time we actually do have a critical value there, but actually occurs when the derivative is 0. And then just like we've done before, plot all those values on a number line. We then need to test our derivative in each of the regions. So we need to pick something smaller than negative 3/2, something between negative 3/2 and 0, something between 0 and 3/2, something that's bigger than 3/2. So I just went ahead and said, well, why don't I plug in -2, -1, +1, and 2? So why don't I do that? Okay. And I've gone ahead and evaluated it. I didn't write down the derivative values, but I did notice the signs. When we're below negative 3/2, the derivative's negative. Between negative 3/2 and 0, you'll find that it's positive. Between 0 and 3/2, we'll find that it's negative again. And when we're bigger than 3/2, the derivative is now positive and will remain positive for the rest of its existence. So just like before, I can mark in red and blue when it's increasing and decreasing. Okay, I can mark that down, and my kitty cat is here right now trying to help me do math, and he's not being very helpful. So now we can write down the increasing and decreasing intervals here. No, Fred, you don't need to type on the keyboard right now. So we can go ahead and notice it's increasing across the blue intervals, which would be negative 3/2 to 0, and be 3/2 to infinity. And then we notice the decreasing, which is negative infinity to negative 3/2, and 0 to 3/2. And now we need to look at our relative maxes and mins. So here we have it decreasing and then increasing at negative 3/2. Now remember, the function has to be defined there. Okay, so as long as the function's defined, so if we can evaluate f of negative 3/2, And it turns out we can. Again, into the original function, not the derivative, we get that that's negative 8.85. And so that's going to be a relative min because it was decreasing and then it's increasing. Okay, so I got a little distracted there with some family things, so I'm back now. So we know that negative 3/2 will be a min. At 0, we see it's increasing and then decreasing. That's the behavior for a relative max. It's required though that the function be defined there. Notice the derivatives is not defined at 0. But if we go back to the original function, yep, we can plug in 0. We can plug in 0, and so we're going to have a relative max there at 0. So we can go ahead and write that one down. And as well, so max there at 0, and as well there at 3/2. It's decreasing and then increasing again. So 3/2, that comes out to negative 8.85. So that's also going to be another relative min. So 2 relative mins there and a relative max. And again, what's important is the original function has to be defined at the point for it to be a relative max or min. It's okay if the derivative is undefined as long as the original function is. So we have our increasing, decreasing behavior, and again our relative maxes and mins.